Hey, Rick.
Hey, Mike, how are you?
Really good.
Am I the first one here?
I think so.
Okay, hold on. I had to update everything and
Oh,
put,
I hate that.
yeah. Uh,
Well, you inspired me to do the oscilloscope one.
I've been reading about oscilloscopes all day, trying to get it. What I'm seeing on the one I've got is that the vertical line doesn't draw. It doesn't, it only draws horizontal lines. So I don't know if something's wrong with it. Anyway, I need to figure out what your timetable is and get down to there and have uh, a known expert look at this foolish thing.
I can do that. So let me just switch screens here really fast. Um,
There we go, a visual.
so is that kind of what you're seeing, just a line like that?
Yep. And if I do the square wave, it's got a little place on the front where you can hook the probe onto it and get the square wave. I get the horizontal lines, but no vertical lines. So I suppose that's okay, but
Um, that actually is probably a brightness thing. Um, if you um, those are the way the scope works is it retraces across. Oops, second here. So on a CRT, it's scanning across and then it's going to jump like that and come back down.
yeah,
Well, if your brightness is really dim, which is okay, um, you're not going to see the really fast small lines. And so if you turn up your brightness a little more, they'll probably show up.
okay. Well, that and I'm trying to put a sine wave into it off this genometer. I don't really have a. It's not a well-known signal generator, and I've got a Radio Shack one too. It was a kit that I didn't put together, but it's supposed to do square waves as well. Anyway, I'll bring all this junk down there. And I realize that for what I've spent on it, I could have bought one of the things off Amazon.
Yeah. Well, and that's where, each one has their usefulness. Um, when you've got, I mean, I've got three oscilloscopes here, four. I've got four oscilloscopes, and I use them differently. This one, this little one here, it's not much of a scope, but it's really good for like training and things like that. And in all fairness, you really don't need a scope to do, and we'll talk about this, but you really don't need it to do radio repair.
Yeah,
Um, I use mine all the time, but to me, I've had one for so long. It's kind of like, just another hand for me.
it has
Uh,
to be there. Okay.
but yeah, we'll get into that and talk, but um, try increasing your brightness a little bit and you'll probably see those vertical lines.
Yeah, I've turned all the knobs as far as they'll go in any direction, and
That's how you use one.
so without success. So I don't know. That's why I need to have you look at it.
Okay, sure. Yeah, we'll talk about this one tonight too.
Yeah, I looked at those on Amazon. They have signal generators built into them and oscilloscope, a multimeter, and so on.
Pretty amazing.
Yeah, I mean for $85, there's a nice one there. What is that?
That looks like a tech.
It says Heath.
I can't read it.
I just
Oh,
put
oh
together
yeah, yeah, yeah.
I put together some Heath kits in my day. We're all locked up. Now we're unlocked.
Oh, good. Myron's here.
Hello.
Hey, I've got a question for you. I want to talk to you. Maybe I can do it before the meeting starts. I'm working with this A1 TV and Electronics, and they've got a low Oslo um, combination receiver and turntable, and the guy has taken the chassis out, rebuilt it all. We cannot get it back in the cabinet. Have you had any experience with that?
I'm not familiar with what you're talking about.
It's a German LOEWE,
Oh, yeah, yeah.
the
Uh,
Oslo. It's interesting because the glass on it is wider than the opening to slide the chassis in. So you have to kind of put it in at a diagonal, and
yeah.
it won't fit diagonally. And so we tried to put actually, Blake came down today to see if he could do it. Because I told the guy, sure, I'll come down. I mean, it's putting a chassis in a radio. How hard
Yeah.
can it be? I spent an hour and I couldn't do it. And then I said, Blake, and he goes, yeah, yeah, I'll come take a look. He was there about an hour, couldn't do it. It's the
Wow.
weirdest damn thing. I think we're going to take a saw to the case to get it in.
It couldn't have somehow gotten swapped with something, right? I mean,
No, supposedly this is the one it came out of, and we've seen pictures. It's the right one. We actually
wow.
checked that.
Yeah, that's good to check.
It's the
Yeah, yeah.
weirdest darn thing I've ever seen in my life.
I'm trying to think. Usually the glass is mounted on the chassis. Yeah.
Yeah, and the problem is they've got some buttons, push buttons at the bottom. Let me just pull it up
Yeah,
here.
piano key thing.
Yeah, let's see.
It's
I think it's like this one. No, not that one.
Hmm.
Can't get it to come up here. Yeah, I think it's that one. No, it's not that one. Oh, that's the Opta. Let's see. It's similar to this. This is the right one. This is an Opta, and that's an Oslo.
yeah.
Hmm.
Uh,
Boy, you would have thought it would just,
yeah, they've got a speaker compartment on this side, one on this side, and this glass actually is wider than the opening, and you just can't put it in diagonally. It's just the weirdest thing.
but it can't come in from the back.
Oh, yeah, we tried to come in from the back. We've tried doing it diagonal. We've tried tilting it. It literally does not fit. It's the strangest thing I've ever seen.
They built the
That's
radio case around the radio after they're done.
Yeah, exactly. Yes. Yeah. I built an airplane in my garage. I can't get it out.
Yeah.
but they got it out.
Uh,
Uh,
So I happened to just before you start this, I happened to pick up I was working on a 1951 Cadillac radio for,
uh-huh.
and it has a scan tuning, right? Which is one of the early signal seeking tuners, right? So I thought that was cool.
hmm.
And it doesn't use a motor to scan. What it does is it has a spring that pulls on it, and then it has like a set of gears, and the gears drive a little paddle wheel so that the air is like a governor. So it prevents
Oh,
it from the spring from pulling it too fast. So spins the little paddle wheel as it goes across the dial. And then when it gets to
Hmm.
the end, it has this giant solenoid that pulls everything back to the left. So it doesn't have a motor, it just has a spring-loaded and governed scanning thing. So I thought that
Wow.
was pretty
Huh.
cool that it didn't have a motor.
I love innovative technology like that. I mean, I just live for that.
I mean, it's electromechanical, right? And so somewhere when it comes along and it has a sensitivity control and it doesn't have manual tuning. So you got to use the sensitivity control to pick the station you really want, the next station or whatever, right? And um, it has a little arm. There's a relay, and then when the relay de-energizes, the arm comes down and grabs the paddle wheel.
Hmm.
Kind of spinning along, and then it comes down and grabs the paddle wheel. But the coolest thing about it, so that was pretty cool, and I was playing with that. It has this thing behind the tuning button that you can push and pull. It turns out it's a vacuum valve that you use to raise and lower the antenna.
Oh my
Oh
gosh.
So
yeah.
yeah,
Huh.
so it has a vacuum driven antenna, but the radio has that as part of the knob. So the radio has these three holes on the side that you hook the vacuum hoses to. One is the vacuum
Wow.
source, and one is the up, and one is the down, and you use that to move the antenna up and down in the car. It's like really cool. So it has a patent number on the side of it, and I looked the patent up, and it was like patented in 1938. Some guy.
Wow.
So it has this little valve head, and when you push it, it opens the valve between the middle one and the one hole, and when you pull it, it opens the valve on the other side. So it pushes and pulls, and so the antenna's just got a chamber with a you can either suck on the top of it or suck on the bottom of it with a little piston inside that raises and lowers the antenna. So it was
I had a car that had vacuum window wipers. I think was that the
Yeah.
International Scout. I can't
Yeah.
remember, but boy, those that sucks so bad.
Well, they had those really until the early 50s and
Yeah,
everything. And
Yeah.
although and of course, you got the most vacuum when you didn't need it. I mean, you didn't have when you opened the throttle full, then you didn't get any vacuum, right? So the vacuum
Hmm.
wiper. And so some cars had like a reservoir, a
right.
jar or something to hold some vacuum so that you could smooth out those times when you didn't have any. And cars actually had sometimes a dual action fuel pump where the other side of it would be a vacuum pump instead of
Right.
using the manifold vacuum.
And I
So,
think what wasn't the Corvettes had the vacuum for the headlights to pop up.
oh yeah, yeah,
Hmm.
I wouldn't be
Hmm.
surprised. Yeah,
You'd go down the road and you'd see all these kind of blinking ones as they're dropping.
totally makes sense. But anyway, I just thought I'd mention that because I'd never seen it before.
Yeah,
And
that's a really cool mechanism.
I was like, what are these holes on the side of the thing? But some of those sets had manual tuning, but this one didn't have it. And Packard was the other car that had this particular radio in it. And so there's a Sam's that has the full uh, theory of operation, which is actually in the Packard description. So uh, I got that Sam. Well, I got the Cadillac Sam's from Mike, not Farabee,
McCrow.
McCrow. Yeah, yeah. He gave me that Sam's, and then it referred to the other Sam's, which I found a copy of online, uh,
Hmm.
which shows how the thing works because you have to basically detect that you're coming into a station before you get centered on it because you can't stop it immediately. So it's kind of got this gain slope detector in it when it basically sees that the level on the station is getting higher, and then that trips the relay, which grabs the paddle, which is an amazing thing. So
Well, I
anyway,
thought tonight we'd talk about oscilloscopes again. This is the same presentation I gave before. Rick kind of inspired this because um, he's fighting with a scope right now. And so I thought I'd kind of go over some of the basics. And then, of course, everybody else can chime in and talk about how they use them or if they do or not, and we'll go from there. So let me do a share here. And I'll even have some demonstrations here. So again, this is going to be really brief, but so what is an oscilloscope? It's really a way of measuring um, voltage versus time. Now, granted, you can do some other things with it, but if you think about it, it's a trace that moves across, and as the voltage changes, this is time this way. So as the voltage changes over time, you're going to see that trace. So if we think about a sine wave, that is centered around zero, you're going to actually be able to watch it um, move up and down. You kind of think of it as like that's the path of the electrons. It's they're going to go down to 0 volts, then it's going to go negative. It's going to hit its maximum negative value. Then it's going to start increasing back to zero. Then it's going to go up again. And so there's a time base, and then there's the voltage scale. Now, you might want to know, well, how come they measure it in time? We think more in terms of frequency rather than time, and I don't want to be doing, dividing by one all the time to figure out, or 1/500 microseconds to figure out what the frequency is. Well, the thing is, it's measuring time, and it does a lot more than just do frequency. It'll do rise time and all kinds of things. So if you wanted to know how long it takes to get from here to here, say on a square wave, you can do that. And that's where the time thing comes into play. In the older oscilloscopes, especially with the CRTs, the the grid is very, very important because when you look at it, you're going to see it's 500 nanoseconds per grid mark. The voltage is going to be I don't see what it's set at here. Oh, 1 volt per division. So you're going to be looking at the volts per division. So this would be 1 volt, 2 volts, probably 2 3/4 volts up, and then negative 2 3/4 volts going down. Um, that's how you can use this. Now, keep in mind the voltage that you're going to be seeing here when you look at this sine wave. Don't confuse the voltage that you're measuring here with the volt you would read on a DMM, because on a standard voltmeter, whether it's a digital voltmeter or analog, that's going to be reading RMS, which is the root mean square. So it's kind of averaging this out, if you will. It's going to be 0.707 times whatever the peak value is. So that number is going to be very different from what you're measuring here. But every once in a while, you're going to want to know what the peak to peak value is or what the peak value is. And then that's where an oscilloscope really is helpful. Any questions before I move on?
Does a sine wave start at the top, or does it start at zero and go down and then up and then back to zero?
That's a great question. And we're going to cover that a little bit more. But the problem you have, actually, maybe what I'll do, I'm going to go ahead and answer that right now. It doesn't do, it does whatever you tell it to.
The only thing I would say about that picture is that there should only be one arrow on the time thing.
Oh, that's true. Yes. Let's see. Can you guys see my video? Oh, if I got to stop sharing. Okay.
Oh yeah, there we go.
So if I'm looking at a sine wave, your question is, where does it start and where does it stop? Where does it start and stop, right? Well,
Right.
if you notice, it's moving all over the place. And that's because I have to sync it. I have to tell it where I want it to start and stop. And we're going to talk about this a little bit more, but that's what the sync pulse does. The sync will tell me, if I can get this thing to sync. There we go. it it's going to tell me where I want the start of the trace to begin. So, that's how I can determine here. Let's see if I change the horizontal. Oops, wrong one. This isn't the greatest oscilloscope. There we go. So I'm telling it where to start, and that's what the whole syncing is, because the waveform doesn't have a start and stop to begin. It's infinite, right? Um,
Mhm.
and so you tell the scope, I want you to start at this point. And you can actually on most oscilloscopes, you can specify, you can move a cursor over on the digital ones and tell it, I want it to start at the peak up here, or I want it to start at the peak down here, or maybe I want it to start at the zero line. So that's a choice that you can make, and then you can make your measurements based on that. So that's a great question. So here, what they're saying, if we look at this, it's actually the peak is, I'm doing a share again. Hopefully you guys can see that.
Hmm.
It's telling it to sync or start the trace right here. And so it's gonna the way the electron beam on the CRT is gonna go, or the same way with the digital. The signal is going to be going across, and when it detects right here, that's the starting point, it's going to start going, and it's going to go until it's off the screen. And then what it's going to do, it's going to wait until it sees this a pulse right at that point, and then it's going to start over again. And
If
to
you
us,
look
it's going to look consistent and smooth.
if you look in the lower right corner, it's telling you exactly where the sink is.
In this case, it's zero. Wait, let's
And
see.
it's rising edge.
Yeah. Oh, yeah. On the rising edge right here. This is telling you I want it to start on the rising edge. We'll talk a little bit more about sync in a minute, but basically you get to choose not only what edge you want it to rise on, but a lot of times you can adjust where it syncs on that rising edge.
Hmm.
And that's useful because what you're going to want to do is line up, maybe like this point with this grid or something like that, so that you can count the grids to see how it goes. With the more modern scopes, especially all the digital scopes, they really make it easy for you, and you don't even have to count grids anymore, because you can actually display things like this where it says, the frequency is 502 hertz. You can pick, it's showing you here what the voltages are and things like that. The old CRT scopes, you can't do that as much. Uh, some of the newer ones you can, but a lot of the really old stuff you can't. But all the digital ones, you get to choose all of that. And that really helps. So not only can you visualize what the waveform is, but you can also get all the statistics that you want for it. Go back to slideshow here. So, what good is an oscilloscope? Well, you can use it to measure voltage. Now, obviously, a DC volt, what you're going to see is just a straight line going across, right? Because over time, the voltage doesn't change. So you're going to just see this flat line. But for alternating current, any type of sine wave, square wave, things like that, you can measure peak voltages. You can look if there's multiple signals in it, you can detect those. You can look at the frequency. You can look at the duty cycle. So that's, if we go back here, this is a 50% duty cycle, meaning this here is the same as this here. Sine waves, they are always that way. But a square wave or a pulse wave, something like a PWM signal, this one might be long and then this one might be short. And so it can actually tell you what that duty cycle is. You can identify noise and distortion on signal. If you're expecting to see a nice sine wave, but you're seeing little blips or you're seeing ringing or fuzziness, that can give you a hint. Sometimes you'll see your signal kind of like moving up and down like this on your scope, and that usually means there's a lower frequency being injected on top of it, like a bad filter capacitor or something like that. So, you might be looking at a high frequency, but it's got this 60 cycle movement going in through it too. You can visualize periodic signals. This is really useful, especially if you're looking at digital things like that. You can actually look at individual pulses that you normally wouldn't be able to see. And a lot of times, if you're trying to measure voltages or something on something that's pulsed or even audio, it's not going to show you anything, but a scope will. The other cool thing is you can measure multiple waveforms. And this is really useful, especially if you have a time-based offset. I don't think I have a picture here, but it would be like if you visualize two of these sine waves, but one of them is staggered a little bit. Maybe it peaks up here and then comes down like this. You can see that offset and detect that if that's supposed to happen or if it's not supposed to happen. And then you could measure the time delay between it. The amount of DC offset. So when we talk about DC offset, a true sine wave, its peak above zero should be the same as the peak below zero. But especially in radio, you can have, say, a bypass capacitor that's passing some DC through it. It's supposed to block the DC, but if it's passing some DC through it, you could actually see this whole waveform shifted off of zero up here. And that gives you an indication, although my signal is there, I've got this DC offset, either positive or negative, that might be causing my problem. And that's, again, sometimes you can measure those on using a analog meter or a digital meter, but it can be tricky to do, and you think you see what you're seeing. It may or may not be that. The other thing is rise time and fall time. If you're looking at a square wave, you should have nice sharp edges, but maybe it's not so sharp. It's taking time to get up there. You can look at that rise and fall time. Those are some of the things you can do with an oscilloscope that's really useful. That's kind of hard to do sometimes with other tools. So the main parts of an oscilloscope, I should stop. Is there any other questions regarding things you can do with an oscilloscope? I mean, there's a lot. You can do XY mode and maybe do FFTs and all kinds of stuff. But anybody have any comments or questions here? Well, let me ask the group, what of the things that for the people that use the oscilloscope, what are the things that you do most often with it? Okay, well, I guess nobody uses one or nobody wants to say.
I have a nice scope, but I find that for working on radios, I hardly ever use it.
Ah, I tend to agree. In a lot of the work that I do, doing repairing all kinds of things, a lot of electronics, I use my scope constantly. But I agree for doing basic radio stuff. I typically don't unless I'm doing some calibration or if I'm looking for hum. That's probably one of the big things I've used it for is looking for hum.
Well, that would be one of my suggested uses is if you changed out the filter caps on a radio, you still got hum coming through it. It would, but instead of changing them all out again, it would be able to find it within a scope, I would think.
It can be. I mean, it can be a little tricky too. Unfortunately, there's a lot of things going on in the radio that sometimes it's hard to find the right spot, but it can definitely help you track things down.
Well, for instance, I've got some LED lights in the place where I've got my radio workroom, and sometimes I believe that there's noise in the AC coming into the radio because of things that are like that, and plus you can pick up the signal up through the antenna of the radio. So is dirty AC in the first place. So it might be a good way to find out where is that dirt coming from.
Yes, it is possible to do that.
Yeah, I did something similar like that just to find the source of noise. And I went around to different outlets, switches and stuff, and I just waved the probe around the switch, and I could see if that's the source of the noise. So
No, I was going
go,
to say the other thing that I've used it, that I've used it for is I fiddle around a fair amount with communications receivers. So as far as looking at, when you're looking at, and mostly looking at oscillators, so that, the old trick of using a transistor radio to find the oscillator in a AA5 is fine, but when you're trying to look at one where the oscillator is at, a much higher frequency, and I've seen there's one instance where I was working on this Hallicrafter's XX25, which didn't appear to be working at the upper band, the highest band, which is like it starts at 25 hertz or something like megahertz, and I couldn't. At first, I thought it was just a switch, it wasn't getting. But then when I put the probe into the oscillator, and I could actually, as it went higher in frequency, even you started the band just below that, and as I cranked the frequency up, the voltage would slowly decay, looking out
ah,
of the oscillator, and then it get to the next band, it would start initially oscillating and then decay again, and it ultimately turned out, he said, you know, it, it's the oscillator tube, which was like a 6X5 or something like this, and it was just putting in a new tube. It was oscillating. It would oscillate at lower frequencies, but when you get up to the higher, it would stop. So the way I could see that was actually, you know, measuring the output from the oscillator on the scope and seeing that what was occurring, and and ultimately it was just the oscillator tube that needed it works fine at lower frequencies, but when you get up to the higher frequency, it was pooping out. So
right.
a new tube was all that it was about. I thought it was something more complicated than that. But anyhow, so just looking at the oscillator, I can see that better with the scope.
Well, John, a tube tester wouldn't pick that up then, would it?
No, it tests fine because it's a really, in terms of the frequency. I mean, this particular older tube was fine at lower frequencies, but when you start pushing it up to its upper limit, that's when you started seeing it pooping out, and it was just that it just needed a new tube. No, it tests fine on a regular tube tester.
Yeah, and one thing about scoping out oscillators, you do have to be very careful because a lot of times the scope probe itself will kill the oscillator.
Well, I don't, you don't even have to, no, but that's true. If you actually connect it to something, you can actually
Right.
just take the probe and put
And
it
be near it.
anywhere nearer.
Yes.
And that's to avoid that problem. I'll just stick it down towards the base of the oscillator tube, not even touching anything, and we'll pick it up.
Right. And you can also take your ground lead from your scope and then do a little loop on it and connect it to the main part of your probe.
Uh-huh.
And that will act as an antenna and it will work really good for doing that type of thing.
Okay.
Uh,
Yeah. Yeah. Again, you're absolutely right. I mean, that's you can really screw it up by actually trying to,
yes.
get into the. So, no. Yeah. So yeah, I've learned that just even, just like you say, just as a antenna, basically just kind of being close to the oscillator is enough.
I,
So
I
one thing
will,
I've, sorry.
I'll demonstrate. I'll show a couple of my little antennas that I built to do that very thing.
One thing I have used the scope for is troubleshooting more modern radios that have digital circuitry in them. Like if there's a little microprocessor or a CPU that has a clock, sometimes the scope can show whether the thing is got a clock signal or whether it's dead. Doesn't give you a great deal of information because you need like a logic analyzer or something for more, but the scope can at least tell you if there's logic activity. on the processor.
Yep. Excellent. Well, thank you guys. So when we look at a scope, there's really just a few parts. You've got the screen to where the waveform is being drawn relative time. You've got your vertical control, and you're going to have typically you can set your control to ground, DC, or AC. So if it's ground, it's actually literally just connecting the probe to ground. So you're not going to see anything. You're just going to see a straight line. If you go to DC, that's directly connected. And I think of AC as an added capacitor, and so it's blocking the DC. So if you're on DC, you're going to actually be able to see your DC offsets, things like that. If you're on AC, it's going to strip off any DC component and you're only going to see the AC. And if you're looking at a DC signal and you're looking for noise, the AC is the way to go because then you can really change your voltage scale really low and look at lots of very low noise amount on your signal.
This is how you can measure ripple on the high voltage BC, B plus.
Yeah. Exactly. And you don't have to look at and have it, jump clear off your screen because it's 400 volts. You just set it to AC. It's going to block that DC voltage, and you're only looking at the ripple. But you've got vertical controls to where you can set where the zero is on your screen. And then you've got your time base, which is your horizontal control. And that's per grid, how many microseconds or milliseconds or whatever there is. And then you're going to have a trigger that you can adjust to determine where you want it to start when it detects a certain spot on the waveform.
I'll close the door.
If you've got a really noisy waveform, you're going to be triggering all over the place and you're not going to get a stable signal. But it's the whole point of the trigger, again, is to where from the left-hand side of the screen as it moves to the right, you want that left-hand side of the screen always starting at the exact same spot. That's what the trigger is doing for you, or a way to think of it.
And if you're looking for AC hum and measuring ripple, most scopes have a line sync, which synchronizes the scope start time to the 60 hertz line frequency. And that makes hum and ripple stay put on the screen, so you can more easily measure the amplitude of it.
Okay, so let's go to the next one. So, we'll talk about trigger a little bit more. A lot of times you're going to see something like this when you first, this is probably a square wave that's trying to be drawn. And you're seeing all this other stuff. That's because it's not triggering correctly. And so it doesn't really know where the start is. And so as the signal progresses from the left to the right, when it starts over again, it's going to be starting at a different spot. So we want to always get it to start at the same spot. And then once you do that, it'll usually clean up and look pretty good. Unless maybe sometimes you have a complicated signal in there, it's supposed to look this way. And that can happen like in CD players I think they call it the eye pattern or something like that. When you're trying to focus the laser and, those kind of things, they actually kind of look like this a little bit. But that's what you're doing here. A lot of times you'll be looking at the relative to the center line, what the positive and negative is, or maybe it starts at zero up here. So you'll be looking at this peak value, and then you're going to try to get it to sync. Sometimes you're going to have really complicated waveforms, something like this, and this can get a little bit difficult to sync because you've got a bunch of different rising edges. If we say sync on a rising edge, it's going to be look for something negative, and when it starts to rise, it's going to sync. Well, it could sync on this one, it could sync on this one, could sync on this one. There's a lot of different spots it could sync on, and so you may see an ugly pattern like this because the sync it's trying to sync on a repeated pattern, but maybe you don't have a repeated pattern. And so some of the newer scopes for sure, like the one I'm going to be demonstrating here, doesn't have a lot of this ability. But a lot of times you can change where your sync level is. So I might, on a pattern like this, I might raise my horizontal sync line right up to just catch right up at the top here, and then I'm going to say sync on a rising edge relative to this spot. And then all of a sudden the pattern is going to start showing correctly and it'll look good because I'm catching the same piece of the waveform every time. If they all go to the same peak, unfortunately, you're not going to have that luxury. But again, it's really about repetitive signals. Now, you might say, well, what if I have a non-repetitive signal? How can I possibly ever sync it? Well, usually what happens there is you use what's called external triggering. Rather than using the internal triggering that Gary was talking about, you would interject an external trigger. And a lot of, like when you're doing sweeps for FM alignment or something like that, most sweep generators will give you a trigger pulse. And then you feed that in as the external input from the sweep generator. And it will say, when I start my sweep generation, say right here, it's going to send out a sync pulse, and then the scope is going to trigger and it's going to start showing that, and it's not going to do it again until it gets to that sync pulse that's externally generated. Most of the time, you won't use an external trigger, but if you're doing something like doing sweeps or that sort of thing, there really isn't an easy way to do it without using an external trigger. But that's kind of like the scope 102. That's the next level of advanced scope work. Most of the time, the internal trigger is going to work fine because most of the time you're looking at repetitive waveforms. So the other nice thing is you can the newer scopes now you can actually have and many of the older ones you can have multi-channels. Some of them you can have up to 4 channels now. A lot of the older scopes you could get up to 2 channels pretty easily, and this is really useful when you're looking at multiple. You say you want to look at the input and the output of something, and you want to see how they relate to each other. As an example, maybe I've got this little sine wave here, and then I've got this pulse coming out. I want to see if it hits at the same spot every time. Are they aligned? And that's where multiple channels can happen. Now, this is where I want to give a really big warning. I should probably put this in the presentation here, but on almost all scopes, there's certain scopes you can get that are very high priced that have it, but almost all scopes, this ground terminal on this BNC, this ground terminal, this one and this one, they're all connected together. So you have to be really careful when you're using an oscilloscope that you don't think, oh, I'm going to go between B minus and B plus, and I'm going to do A minus and A plus, and I'm going to measure those two signals together. If you do something like that to where the B minus and the A minus are different, if you connect both of these, you're going to short out your power supply. And this is a real problem with oscilloscopes. You've got to realize that these grounds are not isolated. And in fact, this ground in almost all oscilloscopes is earth ground. And that's a big deal because especially if you're doing a radio, a vintage radio, ground is not earth ground. And so, if you're looking at connecting this to inside a radio, you could let the smoke out of this thing pretty quickly because usually what happens is your ground lead will just fry instantly. And so you always want to have your device under test on an isolation transformer when you're using an oscilloscope. That way you'll get to keep using that oscilloscope and you won't have to go buy a new one. It's, and that's just good practice anyway. Always have the thing you're working on an isolation transformer, and make sure that you realize that all of these grounds are almost always connected together. There
Ask
are
me how
things like
many probes I've burnt up before I learned that lesson,
so,
or
but
don't.
you do know that now, or it doesn't matter.
Oh yeah, yeah. I before I had an isolation transformer, before I knew how useful and how necessary they were, I had a few accidents.
Yeah,
I've tripped the ground faults, and when I work on stuff in my garage, all those circuits that are on the ground fault interrupters, and I've connecting signal generators and frequency counters and stuff like that when I shouldn't to a radio chassis. You trip and out go the lights in the garage and everything. So,
yep. Do you use an isolation transformer?
oh yeah, now
Oh, now,
I'm
okay.
I'm very careful about this. I haven't done it in a while, but isolation transformer fixes that.
Yeah. Yeah. Everyone working on equipment, please use an isolation transformer. It's not only going to protect your equipment, but it's going to do a better job of protecting you because it also is isolating, you, which is ground, from that circuitry. Um, don't test it, but in theory, if you're on an isolation transformer, you could touch B plus and not get a shock. Now, I didn't say go do it. Don't go do it. But, it's the kind of thing where it can help save your life as well as the life of your equipment. And in fact, test your isolation transformer if you get one. Go between ground and the pins and make sure that it really is isolated. Because especially if you buy the medical ones, they're isolated in a different way. They aren't ground isolated. You have to go in and modify them. And variacs are not isolation transformers. Those are auto transformers. They are not isolation transformers. Do not use one as an isolation transformer.
You can use one in series with an isolation transformer,
Absolutely.
and you must.
And you must. Exactly. Thank you. So a couple other things. Let's talk about probe compensation. So what happens is a lot of oscilloscopes, I think it was mentioned here, a lot of oscilloscopes will actually have a little metal tab sticking out that'll say something like 1 kilohertz or something like that. And that's used, you can use it as a signal generator to test your oscilloscope, but it's also used for testing or setting your probe. Um, Typically, I recommend setting your probe if you have the choice to a 10x probe. Many probes have a little switch on there, 1x, 10x. If you go to 10x, you're going to have like 10 megohms or higher impedance, and so it's not going to be impacting your circuit. I've seen to where 1x will actually impact your circuit. But on 10x, it works pretty good. And what will happen is when you're on 10x, you need to make sure that your probe is compensated because there's a resistor in there, and you've got to there's also a little capacitor in there, and that's what you're typically adjusting here. You get this little probe tool, and if you look in your probe, you'll see this little tiny screw. And what you do is you connect your probe to that little signal generator, or you can use an external one, and you might see a signal like this. Well, that means your probe isn't compensated. And so what you do is you adjust it until you get a square wave. You'll either be undercompensated, you're going to see all this roll off, or you're going to get a spike. And you adjust it to get it as straight as possible. Once you get it as straight as possible, then you know that your scope is in good shape and it's going to give you a nice waveform. I don't believe you can compensate a 1x probe because there isn't anything to compensate. Let's see, we already talked about the using the isolation transformer. Yeah, and it's great for identifying hum on DC, tracing noise, especially if you see like, oh, look, my RF doesn't have noise, but all of a sudden I'm getting it, down later. That'll give you a hint. AM, FM alignment, it can be useful. Visualizing waveforms at pretty much any stage. There are some calibrations on more complex electronics that actually require an oscilloscope. And I have a whole bunch of links in here. So that's the presentation. Not much to it. I just wanted to cover the basics. And I thought what I would do next is share, and we can kind of look at an oscilloscope. I have a bunch of oscilloscopes. This is a cheap little one I have. I think it's only like 1 megahertz, and it uses BNC connectors, or it doesn't even have BNC connectors. Uses banana plugs, and it's only one channel. But I like it because it's small and it's easy to carry around. I'm probably should get rid of it, but one of the cool things is it's still a CRT, and every once in a while a CRT type oscilloscope can come in useful over digital. But let's see. What I thought I would do here is I'm going to use my AM generator I made, turn it on, and we're going to look and see. Now, this scope doesn't have any of the ability to display frequencies or anything. So I'm going to have to count grids, which I don't want to do. But I can look at the waveform. I can see
Mike,
bands. Yes.
Mike, I would expect you could hook a signal generator up and get the same waveform if you wanted to, couldn't you?
Yes, absolutely. Yeah, this is my little AM generator here is just acting as a signal generator.
All right.
And I'm interjecting 1 kilohertz signal. And so, I'm seeing the waveform, and I can expand it. One of the problems with some of the older scopes like this is I have the ability to move this around, but once I start moving around, I really can't tell what the frequency is anymore. Because I can change it here, but now the grid doesn't mean anything any longer. But I can sync it in, and I can look at it. I can vary the height and things like that. If I go look at the RF signal, modulation off, and I look at the RF signal. Now, and if you're new to an oscilloscope, the best way to use it is just start turning the knobs, because you never really know exactly where you should be. I suppose you could sit there and calculate it out, but the easy thing to do is to just kind of flip it around. And every once in a while, flipping around is going to actually give you what you need. So if I flip it around here, let's see, get it to sync. And there's my, waveform. This one is 465 kilohertz. But now let's say I want to modulate this. So I'm going to turn on modulation. So that doesn't look a lot different, but this is where when I start changing the there we go. So as you can see, by changing the scale now, I can see the modulation. So what I'm looking at here is the 465 kilohertz frequency. Let's see if I can zoom in. Maybe I can't. Give it a little bit more gain. So the 465 kilohertz is going up and down like this, right? It's jumping up and down. And then what happens is we're modulating it. So I'm introducing a 1 kilohertz signal on top of it. And so that's what you're seeing here between this peak and this peak. That's going to be 1 kilohertz. So, the 1 kilohertz is inserted on top of it. And so I can actually look at this and see both waveforms. I can see the the 1 kilohertz modulated waveform, and I can see the underlying carrier frequency. Now, if I change my modulation, if I lower my modulation, I go down lower and lower and lower, that little dip part goes away. Or the more I modulate it, this might be like 30% modulated, 50% modulated, 100% modulated. Now I can look at this, and that can be useful. If you're looking at, say, in a radio, you're looking at the before and after the detector, something like that. Because the detector is stripping all of this out. And so I would see something like this before the detector, then after the detector, I'm going to see something more like that. Looks like I'm clipping there. Oh, clipping, that's another good thing that you can look at. So what clipping is, it means I'm overdriving, right? My output drive transistors. What's happening is this is what the sine wave should look like, but when it goes positive and then it goes back negative again, if I put too much drive on there, see how that bottom flattens out? That's called clipping. So that means that I'm overdriving my output. And in audio, that's something you want to look for. If you ever hear, oh, it's being clipped. Well, and in a couple weeks, I apologize, it's taken me a lot longer to get this presentation together. We're going to talk about how to analyze harmonic distortion and things like that in an audio signal. And one of the things is clipping creates a square wave. And well, the interesting thing about a square wave is a combination of a whole bunch of other waves. It's the odd harmonics. And so a sine wave is a pure wave. If you've got a pure sine wave, you only have one signal. But if you have a square wave, you have an infinite number of odd harmonic signals. And so if I start clipping in an audio, well, what I'm really doing is I'm introducing, it's starting to look like a square wave. I start introducing odd harmonics. And so now all of a sudden I'm going to get a lot of distortion in my audio because I'm clipping. And it's just because the drive transistors can't drive that far. And a scope, you can see that. In a DMM, you cannot. And so this is really cool that we can see where it's clipping. And when I designed the signal generator, I actually tuned the transistors or the resistors in the output circuit to where it was just starting to clip, so I could get the maximum drive without over clipping too much. I still clip a little bit, but not much. So, these are some useful things you can do with the oscilloscope you really can't do with anything else. And the way I use the oscilloscope, and I think most people do, is I'm going to be flipping around here, till I can get the signal that I want to see. It's not like, oh, this guy knows what he's doing. No, we all grab the knobs and start twisting until we get the signal that we want. And sometimes you twist again and you'll find a different signal. Sometimes you can get the trace going really slow. Oh, this one won't go that slow. And what you're going to see is that you'll see this little green dot just kind of going across the screen like that. And that can be useful at times if you're looking for noise pulses and things like that. The other thing you can do, this scope can't do it, but some other things you can do is we talked about the external triggering. You can also do one shots to where instead of having it continually go back and forth like this, it only does once. So if you've got really sporadic stuff, you can hang your scope probe on and then do a one shot, and it's going to sit there and wait until the trigger thing happens that you told it to. And as soon as it does, it's going to draw it on the screen, and then it's not going to do any more. And that's really useful for finding really odd type things. Let's see. Oh, I guess the other thing I can do.
Yeah, except if you don't have a storage scope, you lose it right away.
Yeah, exactly. Um, see if I go to. I think I need to pull up my drive a little bit more. There we go. And get it to sync. Oh, I bet I'm exceeding the limit of my scope here. Probably grabbed the wrong scope for doing this. So here what I'm doing is I'm changing the frequency. And as I change the frequency, the spacing between,
Do you have AM on?
yeah, I'm getting all kinds of interference. That's what you get when you have banana plugs for the,
Turn the AM off.
yeah, I've turned off the gain.
Hmm.
Part of it is just the scope too. Let's see, cleaner frequency. Getting lots of distortion for some reason. But I can sit here and change the frequencies, and the distance between the points are going to change as I do it. So all of those kind of things are useful. Now, do you really need a scope? My answer is no. It's probably the last piece of equipment until you get really, really good in troubleshooting. It's not useful, unless you really understand what you're doing. And there, I wanted to show this little thing. I brought it to the meeting this last time. This is a little portable oscilloscope. It's actually 2 channels, 50 megahertz, and it has a signal generator built into it. If I turn it on here, anybody want to guess how much these cost? Thousands of dollars, right?
90 bucks.
Yep,
$50.
$85.
Nice.
Yeah, so there's the single trace scope. And then what I can do, I'm going to plug the signal generator directly in to scope channel 1, go to signal generator mode, turn on the signal generator. And let's see, if I do auto, give me 1 second here. Oh, I think I've got the signal generator turned off. Should be 1 volt per, oh, gotta change the, I've got it set for a times 10 probe. There we go. That's gonna work. But I can actually get a signal on it just by feeding it across. If I want a square wave, I can do that. put in a pulse wave. They're quite amazing. The nice thing is this works as a digital multimeter. If I click here, I have a digital multimeter. If I click and hold here, I get my oscilloscope. If I click and hold here, I get a frequency generator. I can pick all kinds of different waveforms. Really, really nice piece of equipment. I've been shocked how useful it is. I troubleshot a switch mode power supply, and I thought, I'm just going to go ahead and see if I can use just this to troubleshoot the switch mode power supply. Piece of cake. It was really easy. And it's got a really nice continuity mode. If you go into manual continuity, it's really fast. So yeah, I've been really happy with this. The thing is, for 85 bucks, it's kind of hard to go wrong. The nice thing about it also is it's isolated from mains. So I'm not worried at all about, especially with switch mode power supplies, those are really can be quite dangerous because you're dealing with very high voltages and is connected to the main supply. So working with this, being isolated, I'm not worried about blowing things up as I connect my ground and things like that. So, something like this, if granted it's a small screen, but it's two channels, 50 megahertz, which is quite amazing.
So you'd advocate getting one of those rather than trying to restore a vintage oscilloscope or a vintage signal generator or a vintage frequency generator then?
Well, so in my back here, I've got my Rigol oscilloscope, and I've got my nice DMM and my nice signal generator, and I use those on my bench. This isn't going to replace my bench equipment, um, and I use those all the time. But the nice thing about this is when I want to be isolated, I'm going to go grab this. It's a lot cheaper than a differential probe, which is something you can get for an oscilloscope to help protect yourself. But honestly, for what most of us do, this is going to meet all of your goals. It's much better than I thought it would be. I work with Repair Clark County, as you guys know. We go on site and we're repairing things, and I do a lot of the electronic repair, the CDs, CD players and stuff like that. And when you're working on those, it's really nice to be able to use something like this because I can bring this. This is one piece of equipment I can bring, and I can do so much with it. I can use it as a digital multimeter. I can inject signals into it. If I've got a radio or something and I want to, I'm not getting any output, I can take the output of this, feed it to the center of the volume control, and quickly test the whole output section of a radio. So having something like this, so small, portable, to me, it's a lifesaver because I can just carry something like this when I'm working. Even like I was working the other day on actually another it was a subwoofer. Actually, I've got it sitting right over here, and um, I had it too far. I had it sitting on my little roller table, and I was too far away from my other scope. And so I just grabbed this thing because I didn't have to worry about extending the leads. So that kind of stuff is really nice. But for most of the stuff, depending on what you do, um, I think it's great. And I think the average person, especially, as a hobbyist, that's probably all you would need.
Mike,
Yes.
what's the model number of that and what's the source?
So I'll pull both of those up and I'll put them in the chat for you. There's two of them. Let's see if I go to
You see 53T.
yeah, the one I've got is if I go to Amazon.
Yeah.
Yeah, it's the Fnirsi, Fnirsi. I don't get any rebates from any of this, but it's the 3-in-1, and I got the 2C53T. There's two versions. There's a little cheaper version of it, and it doesn't have two scope probes. I got the one that has two scope probes. That one might be the cheaper one. This one 90. The prices went up. I got this one here because it came with the two scope probes. I figured if I had dual oscilloscope, dual trace, the least I should do is get two of them. So it's the Finersi 2C53T. Look for the one with the two scope probes on it. Honestly,
Dave Pidrubecki got one, I think, in the $200 range.
yeah,
A little
and that's the one
larger.
I'll show next. Yeah, so Dave got this one here. No, it's the 21. Oh, I put in the wrong number. 20
Prices probably went up because of tariffs.
O2S. And you want the one labeled S. He got this one here. It's the O1 HDS 2102S. And again, it's a 3-in-1. It actually goes to 100 megahertz, which is phenomenal. The thing of this one is almost exactly the same as the one I've got. The difference is this one is quite a bit bigger. This one measures almost 4 inches wide to where, let me measure mine here.
About 3.
Yeah, mine's like 3.25 or something like
Yeah.
that, maybe 3.5 almost. So it's it's a little bit bigger. And for me, I mean, if you wanted it to be like your bench one, this would be a way to go. Although, it's it's over twice as much money, but you get a 100 megahertz scope. You can kind of see from his hands there. That's probably pretty reasonable what it looks like.
Some
I
of
don't
these, some of the scopes, Mike, are advertised as being automotive scopes. So what's the difference in that?
I think the main thing is they're really selling them to the automotive industry because so much of I noticed that too, and I actually did some looking on YouTube. They're really pushing it for the automotive industry because the automotive guys they need scopes now to go look at the CAN buses and stuff like that, and so they're saying, look, you can go look at the traces on your CAN bus with this. So I think it's more of they're trying to market to them. But
Yeah, and the automotive oscilloscopes also have a lot of like preset features for different things that are very common signal
right.
wise within the automotive stuff.
Yeah, so I mean it's the nice thing is you can use this scope for anything. The one I have actually has more signal generator functions than what this one is. This one's nicer because the screen's a little bit bigger and it's a higher frequency. Although, honestly, I rarely ever even stress my 60 megahertz scope. But it just kind of depends on what you use. Um, whatever you choose, kind of within your price range and how you're going to use it. For me, I wanted something a little bit more portable, a little bit smaller. I saw this one, but I went with the smaller size, and I'm not regretting it. It's working well. Again, I have a few more signal generator functions, but he's got a little bit nicer waveform and a lot faster scope. But I guess what I really wanted to say about these is I don't think you can go wrong. I was kind of shocked when I bought it. I didn't think it was going to be as good as it is. I thought $85, what can you expect? But I was really kind of in a bind where I needed something a little bit smaller. So I thought, well, I'm going to give it a try. and I go, oh my God, it actually works. I was looking at 10 kilohertz clock signals on that power supply, and I could see them really easy, and I could go measure the voltages really quick. I was having a problem to where I couldn't get something working that had to have a signal. I actually injected the signal into the chip to get it to work and go, okay, yeah, I know that the standby is turned on because I can bypass it.
What's
That sort of thing.
what's the highest frequency that the signal generator will make?
50 megahertz also.
Okay.
Yeah, the cool thing about this one that I am hopefully going to use it for is one of the signals that it outputs is DC. And you may go, well, why is that useful? Well, the maximum voltage that you can send out is 3 volts. So I can actually send out a 3-volt DC power supply. This is and I measured it. It looks like it'll go up to about 50 milliamps. So I have a 50 milliamp power supply in this thing also that I can use just by setting the output signal to DC. Now, why is that useful? A lot of digital stuff is 3.3 volts. So I can actually use this to power chips if I want to, and if I have a small section on a circuit board, I can inject the 3 volts into it and then see if I get an output.
Because you're electrically isolated from your piece of equipment you're looking at, you still have to have a isolation transformer on the radio you're looking at.
It's always good to do that for your protection, not only the equipment, because if it's isolated, it's also isolating you from ground, or it's isolating you, which is ground, from the equipment.
Okay.
But yeah, otherwise, if you're dealing with stuff that can't be isolated, this is really handy, something like this, because now you are, at least the scope is isolated. One piece of it is isolated. You still have to be careful being in there because if you get across the hot lead, you're not isolated. So,
Right. Thank you, Mike.
you bet. This is an example of an antenna that I use, just a bent piece of copper wire into a loop. And I'll just connect my scope probe and the ground lead to that. And I can wave that around in a radio and I can detect, RF signals pretty easily. So I just keep this on my bench. I was looking for my other one. I've taken a piece of coax, and what I've done is I've bent it in a little loop like this, and then I've soldered it back together to where the center core goes to ground, and makes a little loop, and then I've got a BNC on the end, and that works really good too. I can move that around and use that as an insulated antenna to identify problems.
Mike, on your copper loop one, could that be insulated copper wire just as
It
easily?
sure could.
Okay.
Yeah.
A little less chance of
Yeah,
spark.
the only thing you don't want is you don't want it shielded, and that's where
Right.
with the coax that I use, I have the shield broken, so I'm not shielding my loop. Let me see if I can find it. It's right here somewhere. I have too many test loops.
So that's the same oscilloscope that I have, but I only know about 10% of it compared to what Mike knows,
It's,
if I'm lucky.
I don't see it here. What did I do with that? Huh. I have to go find my probe. Yeah, I've used an oscilloscope for 40 years or more, 50 years. So, to me, I'm very familiar with them. I'm always using my scope for measuring things, but a lot of that might be the kind of work I do too. But honestly, you don't have to have one for doing radio repair. But when you get in more advanced, it's really useful. Is that the way everyone feels online? That it's not mandatory, but a nice to have if you know what you're doing.
Well,
Absolutely.
it helps understand the risks of buying test equipment at auction.
So for myself, I got to quit buying test equipment. That Hi, my name is Mike. I like test equipment, but um, I do it because I want to fix the test equipment. To me, that's the exciting part is actually working on the test equipment. Um, I have my good at test equipment I use for all of my work, and then I buy all this crap or pull it off the free table, and then I try to get it working. And that's the fun and the challenge.
Sure, certainly a challenge.
Yeah. Because honestly, most of that stuff, like this little scope I've got sitting here, or I've got another one sitting over there that's a CRT. I I never use them. The only time I've used this little one that I was showing you was I had brought it to a couple repair events. But now that I've got this little meter, I'm not going to bring that to a repair event again. Um, because then I still had my meter, and I've got those tweezers. I use those tweezers all the time. Oh my God, those are the best thing in the world. I showed you guys the tweezers, right?
Yeah. Yeah. I bought some. That's great.
Yeah. Did you get the SP2s or the SP1s?
I don't remember. Uh,
Let me just share again. Yeah, I use those things. Oh my God, all the time. The best part about them. Let's see. Yeah, this is the new one, the ST2. The great thing about them is you can actually measure ESR and capacitance in circuit on most things. I'm constantly measuring stuff in circuit, and they're just dead on. I just got done working on a. Have you guys ever seen a Zeppelin Air? Let me show this to you. It's a it's an iPod speaker. This thing is huge, and it's heavy. It's got a huge subwoofer here. It's got two mid ranges and then two tweeters, and it was built back in I think like 2000 range, and they were like $800 or $900, um, and the sound quality is amazing on them. And I just had one in for repair. Um, 18 dead capacitors in it. Um, all of them were high ESR, and I found them all with the tweezers. Um, and I take that back. I found about seven of them with the tweezers, and I said, "Screw it, I'm replacing all the capacitors." And after I pulled them, yeah, all but one was bad. But the original ST1s, you couldn't disconnect um, the tweezers from the unit. But the ST2, they made this to where it's like um, what is it? It's where's the picture? There it goes. You can plug in wires into it, and then they give you Kelvin clips, which anybody getting one of these for doing vintage radios, I recommend getting the ST2, um, because this will allow you to go across wider capacitors and things like that. But the great thing is because they're measuring using high frequency, and the frequency you can set between, I think it's 100 ohm or 100 hertz to, I think on these it's 100 kilohertz. Um, you can actually measure in circuit. And so you can just, connect these right across your caps, and it'll tell you what the capacitance and the ESR is. And that is, I'll tell you, a huge time saver. And then, for circuit boards, I just use the tweezer part, and I can just walk across things. The other nice thing about it, if you're measuring resistors or anything like that, you can just go right across them and it'll tell you what they are in circuit most of the time. But yeah, these things are absolutely amazing. So Doug, you've got them and you like yours?
Yeah, I like mine, but I got the ST1, so now of course
Oh.
I'm gonna get the ST2.
Maybe you and I ought to sell our ST1s to somebody that wants one, and we'll go get the ST2s.
Yeah.
Put them up as uh, club prizes or door prizes or something.
Or a swap meet coming up, so
Yeah, there you go.
yeah.
But yeah, I got to tell you, when you're measuring caps, especially if you're looking for leaky caps, especially ESR, boy, you can't beat being able to just go in circuit and check, 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 or resistors. I was trying to match some resistors for a piece of test equipment I had, and I had one of the paper rolls with all the resistors on there, and I was trying to find one that was like 99 ohms because it was a multimeter that had one of the precision resistors, and I just ran that the tweezers right across the paper things, going boop boop boop. Oh, that one's 99, and grab it. It made it really fast. It's so much easier than trying to hit it with the meter and it's moving all around, and that kind of thing.
I was looking for a small value capacitor in this big bag of miscellaneous capacitors I think I got off the free table, and all the little fine print and that. And so at some point I just, oh, these are right about the right physical size. And I just went at it with the meter and until I found the one that was close enough.
Yeah, yeah, they're amazing. I mean, it's to me it's phenomenal the tools that are available today for the at the price. I mean, my gosh, you can do so much today what was such a struggle years ago. Well, that's about all I have on oscilloscopes. If anybody has any other questions or comments or want to relate your stuff, I know it wasn't really intense, but it's hopefully a kind of an introduction and make you think about some different things a little bit.
That was really great, Mike. Thank you.
That was good.
Yeah,
Yeah,
excellent.
thanks.
Yeah.
And I promise
Yeah, thank you, Mike.
I'll try to get to that harmonic distortion and audio analysis as soon as I can. I started putting a presentation together, and it just keeps growing because I go, oh crap, I got to explain this. Oh yeah, I better explain that. So I don't know. That might be a two-parter.
Once upon a time, I worked with some musicians that wanted distortion in amplifiers. And I think a 12AX7 or something like that in the front end of the amp. They wanted, how do you make them distort? How do you make them overdrive? It was a desired sound.
Yep. Well, I think the simplest explanation is a pure amplifier should take a small input signal, and the only thing that should happen on the output is make it larger. It should not change it at all. And distortion is anything that is a change from the input other than the amplitude. So yeah, there's a lot of ways you can distort. You can do phase distortion and harmonic distortion. There's like it's 6 or 7 different classifications that they use.
Yep.
And I'm trying to figure out how to do that without getting too in depth, but still be useful.
Well, they make amps. I even had one that had a distorted channel on it. You just turn the switch and it would sound real fuzzy, but that's what they wanted.
Let's turn it up to 11.
There you go.
Mm-hmm.
Anyway,
When
thanks
when I
again,
was
Mike.
when I first got started working, I ended up starting up my own business. I did a video game repair business on the side after my day job, and it started out. I bought an old pinball machine and I got it working. I thought that was really cool. Then I started talking to some of the game rooms and stuff, seeing if they had any other ones because I I wanted to get another one. Next thing I know, they said, "Oh, you can fix them." And so I started working on them, and then I ended up having my own business. And one of the cool things you could do with like the asteroids game, um, it's actually the asteroid screen is nothing more than an XY vector display. And so you can take the X input into your scope, take the Y input into your scope, put it in XY mode, and you can actually sit there and play asteroids right on your oscilloscope. That was a lot of fun. That's how a lot of times I'd test that the monitor was bad. Is I'd just put my scope up 2 channels up to it, put it in XY mode, and I could see it's working there, so I knew it was a monitor problem or not.
Do that with your handheld now.
Yeah, and I can do that with this too. Yeah. In fact, there's all kinds of stuff people have done with the microcontrollers, the Arduinos, to where they create picture displays for oscilloscopes. Where you can display your name or anything like that, and in XY mode, it'll just output it with the right voltages on each one to display your picture.
Um,
All right. Well, thanks everyone.
Yeah, thanks again, Mike.
Yeah, thanks, Mike.
Thank you.
Thank you, Mike. Very good.
Good night,
Peace
all.
out.
Yeah, good night.
Have a good night.
Thanks, Mike. If you get a chance, can you put up the information that was requested in the chat?
Oh, I'll do that right now. Sorry.
Thanks.
Uh, Actually, let me grab the I'll grab the link straight out of Amazon too. See, the one I just put in is the one that Dave Pedrebecki bought. Very nice unit, just a lot more expensive.
I think I'd prefer the cheaper one.
And let me find the one that's got the 2 probes in it. Yeah, I like the cheaper one mainly just due to the size, but and that's the other one. And I'll put in the tweezers too.
Yeah.
Let's see. I think it was this one. And that's the tweezers. That's the ST2, which is the new one with comes with the Kelvin clips in it. The other one, the ST1, is a little bit cheaper. And they work great. Let's see, the ST. One's only $29. I would get
To last a long time on it too.
Oh yeah. And what I like about it also is the back is magnetic. And so I just have it stuck on the side of my shelf, which is so easy to just go grab and pull. Yeah, I'm not saying these are the best in any of them, but it's what I found, and it's working well for me. And honestly, I don't know if you can go wrong on most of this stuff. It's just don't expect too much out of it, and you'll do well. You know, like this one will do um, um, I can't think of the name of it. Fast Fourier transform FFTs. It'll do FFTs, but the FFT kind of sucks on it because you get this little tiny picture-in-picture screen. Actually, I'll show it here. The little purple screen is your FFT screen. Now, what FFTs are is fast Fourier transforms, and it's telling you, starting from the left to right, what your fundamental frequency is, and then all the other frequencies in the spectrum that it can see. You know, kind of like a spectrum analyzer. But the problem is you don't have the ability to see what the frequencies are. So the fact that you can't see them, you know, you can see that there's something else there. And actually, let me just feed the input. Oh, that's kind of cool. Let's see. Let me go back to square wave.
Hey, Mike,
Yeah,
you probably have one of those tiny SAs, tiny spectrum analyzer,
I do.
and a tiny network analyzer.
Um, I just what I've got is a software defined radio. Um, so here you can see that. So the signal I got going in there, it's showing that I've got a peak here and then there's nothing and I got another peak over there. That doesn't really tell you too much, but you know, it does show that there is some other things going on. You know, it's not just a single peak. If I go to a sine wave,
Looks like an AC coupled square wave.
let's see. Now, if I go to a sine wave, you can see I've got a really pure looking FFT. So I'm not seeing a lot of other stuff going on. So that part's useful, but you know, it's not the most useful FFT that you would ever hope for. Let's see, off. But like I say, it's, you know, you got to realize the price point, realize the, you know, what the capabilities are, and you can still get a lot out of it. And it's actually a lot better than probably the CRT scopes I've got laying around here. All right, cool. Well, I'm going to take off.
All right, sounds good. Thanks again.
You bet.
Take care.
Thanks.